In this video, we solve problem 15.R.021 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're given a field. This is its x component, this is its y component, and this is its z component. We're just asked to compute the divergence and the curl of the field. So just remember, whenever you're computing divergence, you should always get a scalar. And that scalar comes from taking the dot product of the del operator with f. Now the del operator is not a vector, but it acts like a vector. It has components that are partial derivative operators with respect to x, y, and z. So I'm using that, and I'm taking the dot product with f, and f has components m, n, and p. That's the notation we've been using in our class. So our x component is denoted by m, our y component is denoted by n, and the z component is denoted by p. And then we treat this like a dot product. And the only difference is where we would traditionally multiply in a dot product, every time we would traditionally multiply, we are operating instead. So what this says is we want to take these two guys, and normally I'd multiply them. Instead, I'm going to take the partial derivative with respect to x of the x component. And then I'll add the partial derivative with respect to y of the y component. And then I'll add the partial derivative with respect to z of the z component. And our x, y, and z components are right here. So it looks like multiplication, but it's just operating instead. And remember, dot products always give you scalars. So when we're done, we should get a scalar function. You should not get a vector from the divergence, because you multiply and add, multiply and add, multiply and add when you take a dot product. With the del operator, you're going to operate and add, operate and add, operate and add. Okay, now we're taking the partial derivative with respect to x of this. Now remember, whenever you take a partial derivative, you treat all of the other variables like constants. So this cosine of y doesn't have any x's in it. The derivative is, so I'm treating it like a constant. The derivative of a constant with respect to x is 0. Now this is a little different. Y is being treated as a constant, but I don't just have a constant here by itself. I have a constant times a function of x. Remember, the derivative of a constant times a function of x is that constant, so you bring it down, times the derivative of that function of x. The derivative of cosine of x with respect to x is negative sine of x. And then we add the partial derivative of this with respect to y. There's no y in that, so that's all constant with respect to y. Derivative of a constant is 0. And then the x is being treated as a constant here, so we bring down our constant, which is negative x, and then we differentiate sine of y with respect to y. Derivative of sine of y with respect to y is cosine of y. And then on the last one, x and y are being treated as constants and z is our variable. So this is the derivative of a constant times z. The derivative of a constant times z is just the constant. So that's our answer. I probably wouldn't leave this plus negative x times cosine of y. I would simplify that this way. And if you want, you could put the xy first because it's a positive term. That's our divergence. Now finding the curl of f is similar, except everywhere, or where here we're taking dot product with the curl, we are taking a cross product with the del operator. Now the curl of f yields a vector. And we can write this in this determinant form. So we have I hat, j hat, and k hat in the first row, and then those partial derivative operators in the second row, and the components of f in the last row. F is pretty long, so I'm just going to do one column at a time. The x component of f was cosine of y. plus y times cosine of x. And then in this column, we'll have j hat, the partial with respect to y operator, and then the y component of f, which was sine of x minus x times sine of y. And the last column will have k hat, the partial with respect to z, and the z component of our field. So that's that. So notice you have I hat, j hat, and k hat, the del operator in the second row, and the third row you have m, n, and p, the components of your field. Now you evaluate this the same way you evaluate a cross product. So you cross out the row and column containing I hat, and you say I hat times this 2 by 2 determinant. That's what we would normally do. But now instead of multiplying, instead of doing this times this and subtracting this times this, we're operating. So we're taking the partial derivative with respect to y of x times y times z. And then we're subtracting the partial derivative with respect to z of that. And all of that gets multiplied by I hat, so that's the x component of our curl. And we'll compute that in just a moment. And then we do the same thing with the y component. You just multiply this one by -1. So we'll have -1 times j hat times, cross out the row and column containing j hat. And then we would traditionally do a 2 by 2 determinant, but instead of a 2 by 2 determinant, we're operating. So this is the partial derivative with respect to x of x times y times z there, minus the partial derivative with respect to z of that component. Oops. There we go. Oh, and then the last one, it looks like I don't have enough space, so I'm going to cross out the row and column containing k hat, and I want this partial derivative minus that partial derivative right there, but there's not enough space. So I'm going to change my notation a little bit. This was all of this times I hat, minus all of this times j hat. There we go. That's my x component minus my y component, and then the z component I'll do in the next line, plus the partial derivative with respect to x of this expression. So that's x sine of y, minus the partial derivative with respect to y of that expression. And then you just evaluate those partial derivatives. Now remember, you're treating the other variables as constants, and you're differentiating with respect to this variable here. So this is a constant times y. The derivative of a constant times y is just the constant, and the constants in this case are x and z. Here, there are no z's, so all of this is constant with respect to z. The derivative of a constant with respect to z is 0. Here, I'm thinking of x as my variable and y and z as constants. So this is the derivative of a constant times x. The derivative of a constant times x is just the constant, y times z. And then we're taking the derivative of all of this with respect to z. There are no z's, so the derivative of this with respect to z is 0 because we're treating the whole thing as a constant. Now this part is a little bit more involved. I'm taking the derivative of sine of x with respect to x. That's cosine of x. And then I've got a negative x times sine of y. Remember, y is being treated as a constant here. So this is really just a negative x times a constant. So what's the derivative of a constant times x? It's just the constant, and that constant is sine of y this time. Okay, now we're subtracting all of this. We take the derivative with respect to y of cosine of y. That's negative sine of y. And then we're taking the derivative with respect to y of y times cosine of x. Well, cosine of x is being treated as a constant because we're differentiating with respect to y. So this is the derivative of a constant times y. So we just get the constant. And you can distribute that negative. Distribute the negative here and there. Those reduce, and it turns out we get 0. Okay, so our x component is xz. Our y component is a negative yz. And our z component is 0. So this is what the curl looks like in component form. And in terms of our standard unit vectors, I hat, j hat, and k hat, we'd have xz times I hat minus yz times j hat. And there's no need to add 0 times k hat. So that's how we compute the curl. It's the cross product with the del operator, and it yields a vector. When we're computing divergence, it's the dot product with the del operator. It yields its scalar function of your variables. If we're in 3 space, it's variables x, y, and z in general.